Welcome, curious minds and sleepy thinkers. You've found a soft place to land, a quiet harbor where the questions are vast and the pace is slow enough not to jolt you from your pillow cocoon. Tonight, we're going to gently drift into one of the most mysterious corners of our solar system, a place that for centuries played a cosmic magic trick. We'll ponder a celestial body that seemed to appear and disappear at will, a moon that truly vanished before our very eyes. But don't worry, we'll take it slow. This isn't a race through equations or a frantic dash across the stars. It's more like floating through a galaxy of ideas with a warm, comforting cup of chamomile tea, letting the gentle currents of thought carry us where they may. Our story, this quiet journey into the heart of a cosmic enigma, begins not with a sudden revelation, but with a persistent puzzle that challenged even the keenest observers of the night sky for generations. Imagine, if you will, the early days of astronomy when telescopes were mere windows, small and imperfect, peering into the vast, shimmering darkness. It was a time of discovery, certainly, but also a time of profound bewilderment, as the heavens often held secrets that seemed to defy the very laws of logic, whispering riddles into the ears of those patient enough to listen. And among these celestial enigmas, few were as perplexing as a certain moon of Saturn, a world known to us today as Iapetus. In those distant epochs when the tools of observation were rudimentary by modern standards, yet wielded with extraordinary dedication, Iapetus routinely appeared to vanish from sight, entirely a true specter in the cosmic theater. It wasn't a rare anomaly, a fleeting atmospheric distortion, or a momentary lapse in focus. No, this was a scheduled performance, a recurring illusion that left astronomers, those tireless sentinels of the night, scratching their heads, peering through their brass and glass instruments with a mixture of frustration and awe. Some nights, it would be there, a faint, resolute point of light, holding its lonely vigil beside the majestic, ringed giant Saturn. Its presence was subtle, a mere glimmer, yet undeniably there for those who knew where to look. And then, without warning, the very next night, or sometimes just a few nights later, it was simply gone, vanished, like a whisper on the wind, leaving behind only the lingering question of its absence, a hole in the familiar cosmic tapestry. This wasn't merely a point of light winking out. It was as if an entire celestial body, a substantial moon, had simply decided to step out of existence. This was, in essence, the ultimate magician's trick performed, not on a stage bathed in theatrical lights, but across the immeasurable distances of space, using the very fabric of the cosmos as its grand illusion. For those dedicated souls who spent their nights at the eyepieces of their telescopes, meticulously charting the positions of the known celestial bodies, watching the silent ballet of the planets and their retinues, this disappearing act was maddening. They would prepare for their observations, knowing where each moon should be, and then, without warning, one of the principal dancers would simply step out of the spotlight, leaving an empty space where moments before a moon had been. It was as if the universe itself was playing a subtle joke, a gentle tease to remind humanity of its humble yet persistent place in the grand scheme of things. The consistency of its vanishing act, the regularity with which it would reappear and then retreat into invisibility, suggested something far more profound than a simple error or an atmospheric quirk. It hinted at something inherent to the moon itself, a fundamental property that dictated its peculiar dance of presence and absence. Astronomers would share tales of its fleeting presence, of the nights spent fruitlessly searching for its faint glow, only to find it again days later, as if it had simply decided to return from an invisible voyage. This quiet challenge hung in the celestial air, a constant invitation to delve deeper to unravel the cosmic secret. But as humanity slowly and painstakingly began to figure out how this cosmic vanishing act was done, the mysteries of Iapetus, far from diminishing, only grew deeper, more profound, and infinitely more compelling. The simple explanation, once it began to emerge, didn't provide a neat, tidy closure. Instead, It opened doors to far more intricate and compelling questions, revealing layers of complexity we had barely imagined. It wasn't just a matter of visibility. It was a testament to the moon's profound and startling contrasts, to a duality woven into its very being. Imagine if you can a world divided with such stark clarity that it seems to be two entirely different places stitched together, a cosmic patchwork of extremes. One half of Iapetus, as we would eventually learn through the patient gathering of scientific data, is plunged into near absolute darkness. This region is a shadowy realm, a canvas painted with the deepest hues of night so profoundly dark that it absorbs almost all the light that falls upon it. It is a place of whispers and deep quiet secrets, where light itself seems to be swallowed whole. And then, in breathtaking, almost unbelievable contrast, the other half gleams with the brilliance of reflective ice, a dazzling expanse that shines with the pure, untainted light of a fresh snowfall, a beacon in the cold emptiness of space. This isn't a subtle gradient or a gradual transition like the fading light of a sunset. No, it's a dramatic, almost theatrical division, a stark, almost impossibly sharp line drawn across the face of a world, as if an artist had decided to illustrate the very concepts of light and shadow on a single, colossal canvas. And as if this wasn't enough to pique our cosmic curiosity, to make us ponder the extraordinary variety of worlds that drift through the void. Imagine an additional feature, a truly astounding geographical marvel that defies easy explanation. Around its equator, like a stony girdle wrapped precisely around its middle, lies a colossal mountain range. This isn't just a few scattered peaks or a gentle undulation of the terrain. No, this is a monumental wall, a vast uninterrupted barrier of rock and ice that stretches for immense distances, its origins utterly defying conventional understanding. Why, we might softly ask ourselves as we consider this strange world, does this moon present such a dramatic, almost two-faced characteristic? What profound imbalance, what ancient cataclysmic event, or what slow, inexorable process unfolding over eons could have sculpted a mountain chain taller than Mount Everest in a place that, by all accounts, should be a relatively simple sphere of ice and rock spinning quietly in the cosmic dance? These are the kinds of questions that Iapetus whispers across the vast distances, drawing us closer, inviting us to ponder not just its own unique story, but the turbulent youth of our very own solar system, the chaotic formative years that shaped all the worlds we know. This distant world, with its vanishing act and its impossible mountain, holds secrets not just about itself, but about the primordial chaos and formation of everything we know, a frozen echo of cosmic creation. The journey to understand Iapetus, Saturn's third largest moon, and arguably its most enigmatic, truly begins not with grand space probes or distant radio signals, but with the keen eye and persistent spirit of an extraordinary individual, Giovanni Domenico Cassini. Imagine the year 1671, a time when the universe was still largely a realm of philosophical conjecture and mythological storytelling, slowly, gradually yielding its secrets to the patient gaze of early scientists. Cassini, a man of meticulous observation and profound patience, stood at the Paris Observatory, peering through the long, slender tubes of refracting telescopes. These instruments, marvels of their age, were primitive by our standards, yet they represented the cutting edge of human ingenuity, allowing a deeper penetration into the celestial sphere than ever before. And in that year, as his eye was pressed against the eyepiece, patiently scanning the familiar skies around the majestic ringed giant Saturn, Cassini spotted it a new point of light. It was just a tiny, faint speck, barely discernible against the inky blackness, yet it was undeniably there, holding a steady, purposeful orbit around the distant planet. Its discovery alone would have been a triumph, a testament to the expanding reach of human perception. But almost immediately, this new moon, this faint glimmer, behaved strangely. It wasn't content to simply follow a predictable circular path. like a well-behaved cosmic satellite. Instead, it had a mysterious rhythm all its own, a peculiar dance that puzzled its human observer. When it was observed on the western side of Saturn in its orbit from our perspective here on Earth, it was reasonably visible, a faint but discernible dot, a resolute presence, clinging to the edge of Saturn's grandeur. But as it traveled on its orbital journey, slowly moving to the eastern side of the planet, something truly peculiar happened. It seemed to vanish. Not quickly, not dramatically, but subtly, gradually becoming incredibly faint, often disappearing entirely from view in those relatively humble telescopes of the 17th century. It was as if the moon itself was playing hide and seek with the astronomers, a cosmic game of peekaboo that defied the logic of consistent observation. Cassini, with his calm and systematic approach, was not one to jump to conclusions or dismiss an anomaly as mere error. He meticulously reflected on his observations, noting the consistent pattern of its presence and absence. He even made a remarkable note, detailing the frustration of its elusive nature sometimes. He remarked, after having begun to disappear with the 32-foot telescope, it had been sought in vain the next day with one of 45. This was not a small detail. He was stating that even a larger and more powerful instrument, a testament to the cutting edge of optical technology at the time, failed to recover the moon once it had begun its vanishing act. The moon was truly defying the best technology and the most patient observers of the day. This consistent, perplexing behavior, this silent cosmic magic show, led Cassini to a truly astonishing conclusion for his time, a deduction that was revolutionary in its insight into the nature of celestial bodies. He reasoned that for the moon to appear and disappear in such a precise orbital fashion, it must possess a striking asymmetry. One hemisphere, he deduced, had to be significantly darker than the other. Imagine a cosmic sphere painted half with brilliant white and half with deep, absorbing black. But this wasn't all. Perhaps even more remarkably, he concluded that this moon must be tidally locked to Saturn. To understand tidal locking, think of it like this pictured two cosmic dance partners. One, the larger, more massive partner, is Saturn. The other, the smaller, more agile one, is Iapetus. As they dance around each other, gravitational forces between them create a kind of invisible tether. For many moons, this tether causes them to slow their rotation over vast stretches of time until they reach a point where their rotational period perfectly matches their orbital period. This means that, like a steadfast cosmic companion, Iapetus always keeps the same face towards its planet Saturn. Just as our own moon faithfully presents the same familiar face towards Earth throughout its orbital journey. It's a delicate balance, a frozen spin where one side forever gazes at its primary, while the other looks out into the deeper void. This insight was crucial. It meant that as Iapetus journeyed around Saturn, slowly tracing its vast orbital path, it would alternate in presenting its bright face and its dark face towards Earth from our vantage point. When the bright side turned towards us visible from our perspective on the western side of its orbit, it was discernible, a faint but steady light. But when the dark side rotated into view, positioned on the eastern side of its orbital path, it faded from view, becoming almost indistinguishable against the blackness of space itself. It was as if a cosmic lantern had a bright pane and a darkened pane, and as it orbited, it would present one or the other to us. The light from the dark side was simply too faint for the 17th century telescopes to gather. This was an astonishing observation for the 17th century, a testament to Cassini's genius and the power of careful deduction. It wasn't just about spotting a new moon, which itself was a monumental achievement. It was about inferring a fundamental surface property of a distant world, a characteristic that spoke volumes about its very nature without ever truly seeing it resolved as anything more than a tiny pinprick of light. It marked the very first surface property ever detected on a planetary moon outside the Earth-Moon system. Before Cassini, our understanding of other moons was largely limited to their orbital paths, their movements, and their simple presence. But with Iapetus, he unveiled a hidden dimension, a glimpse into the diverse and complex worlds that lay beyond our immediate reach, suggesting that celestial bodies were not uniform spheres, but unique individuals with their own distinct characteristics. It was a revelation that opened up new avenues of thought, hinting at the vast unexplored complexities of the solar system. It was a profound step in human understanding, a testament to the power of human intellect, observing subtle clues, patiently gathering fragmented data, and weaving them into profound truths, long before spacecraft could venture forth and confirm such audacious ideas. Cassini, in his time, a man whose contributions laid foundational stones for modern astronomy, named the 4 moons he discovered Sidera Lodoicea, or the stars of Louis, in honor of his patron, the powerful King Louis XIII of France. This was a common practice of the era, linking celestial discovery with earthly patronage, intertwining the pursuit of knowledge with the political and social currents of the time. These names, however beautiful and historically significant as they were, didn't quite stick in the grand narrative of astronomical nomenclature. Like many early designations, they eventually faded from common use, making way for names that perhaps better captured the essence or the mythic resonance of these distant worlds' names that would resonate with broader cultural narratives. Centuries later, as astronomical knowledge deepened and the pantheon of celestial bodies grew, a new suggestion emerged from the celebrated astronomer John Herschel, son of the equally famous William Herschel, who had discovered Uranus. John Herschel, with a nod to classical mythology, a rich tapestry of stories that had long been intertwined with the names of planets and constellations, proposed names from the Titans. These were the primordial powerful beings, the brothers and sisters of Saturn, known as Cronus in Greek mythology, who preceded the Olympian gods. It was a fitting choice connecting these distant worlds to the ancient powerful forces that were believed to have shaped the cosmos, and thus for this peculiar vanishing world, the name Iapetus was chosen. In mythology, Iapetus was a Titan, one of the original 12, and was famously the father of Atlas, who bore the weight of the heavens on his shoulders, and Prometheus, the cunning Titan, who famously defied the gods by gifting fire and knowledge to humankind. By extension, Iapetus became associated with the father of Prometheus's creations, humanity itself with its striving, its curiosity, and its endless quest for understanding. This moniker Iapetus seemed to fit this enigmatic moon, perfectly imbuing it with a sense of ancient mystery, a connection to the very origins of things, and a subtle nod to the enduring human quest for knowledge, much like Prometheus's quest for enlightenment, a quest that mirrors our own journey to understand this strange, two-faced moon. It was a name that resonated with the profound questions. The moon itself posed a name that felt as if it had been waiting for its celestial namesake, carrying the weight of ancient myth and the promise of future revelation within its syllables. A name that perhaps subtly hinted at the enduring human need to categorize, to name, to bring order to the boundless chaos of the cosmos, even when the secrets remain deeply, beautifully hidden. For centuries after Cassini's groundbreaking deduction, Iapetus remained steadfast in its cosmic performance, little more than that intriguing point of light, consistently exhibiting its bizarre brightness variation. It was a known anomaly, a cosmic curiosity whispered about among astronomers, a persistent, quiet challenge to our understanding. But its true nature remained shrouded in the vast, unyielding distances of space. Earthbound telescopes, even as they steadily improved through the Enlightenment and into the Industrial Age, simply lacked the resolving power, the keenness of vision to truly pierce through the veil of light years and see the surface features, to truly confirm with direct observation the dark and bright hemispheres Cassini had so astutely inferred. It was a patient wait, a testament to the slow, inexorable march of scientific progress, a quiet longing for the day when humanity could get a closer, clearer look. Imagine the frustration, the tantalizing closeness of a mystery, yet the profound distance that kept its secrets. Each new generation of astronomers would turn their ever larger lenses towards Saturn, hoping to finally discern the truth of Iapetus's vanishing act. They would sketch its orbital path, note its dimming and brightening, and reinforce the deductions of Cassini, but the moon's surface, the very canvas of its peculiar characteristic, remained a featureless blur, a distant, enigmatic whisper. It was like hearing a beautiful, complex melody played from across a vast valley. You could discern the broad strokes, the dominant themes, but the intricate notes, the subtle harmonies remained frustratingly out of reach. This enduring nature of its mystery served as a quiet, persistent challenge, a low hum in the background of astronomical study, beckoning future generations to continue the quest. The anticipation for a truly intimate glimpse, a moment when the distant blur would sharpen into detail. Quietly built over centuries, a cosmic promise waiting for the right technology to unlock it. Then came the late 1970s and early 1980s, an era that truly revolutionized our understanding of the outer solar system, a golden age of exploration. This was the age of the Voyager probes, humanity's first intrepid emissaries to the gas giants and their sprawling retinues of moons. These robotic explorers, launched from Earth with grand ambitions and the cutting edge of contemporary engineering, embarked on journeys of unprecedented scale, conducting distant flybys of Saturn and its majestic companions. They were designed not just to visit, but to truly see, to gather data that could only be obtained by venturing far beyond the Earth's gravitational embrace. As they soared through the frigid vacuum of space, they offered tantalizing, albeit often fleeting glimpses of Saturn's moons, transforming them from mere points of light into worlds of burgeoning complexity. Voyager 1, in its remarkable journey, a grand tour of the outer planets, managed to capture images that for the first time clearly showed the stark dark brightness difference on Iapetus. This was a monumental moment, a profound validation. Imagine the quiet thrill, the deep satisfaction of seeing a hypothesis conceived centuries earlier, through patient observation and brilliant inference by Cassini, finally undeniably validated by direct visual evidence from a robotic explorer sailing billions of miles away. It was a bridge built across time, connecting the sharp intellect of the 17th century with the technological prowess of the 20th. The images, though distant, showed unmistakably that Iapetus was indeed a world of two halves, one significantly darker than the other, just as Cassini had predicted. It laid to rest any lingering doubts about the moon's unique albedo variations. However, the resolution of Voyager 1's images, while groundbreaking and immensely informative, wasn't high enough to reveal the intricate details that scientists craved, the subtle textures and precise boundaries that would truly tell the moon's story. It was like seeing a beautiful, complex tapestry from a great distance. You could discern the broad strokes, the dominant colors, the overall pattern, but the fine threads, the subtle variations in, weave the true artistry, remained hidden. The images were compelling, a tantalizing peek, but they left much to the imagination, much to be discovered. Voyager 2, following a slightly different trajectory, was afforded a marginally closer pass to Iapetus. This closer encounter, though still distant by future standards, gifted us with our first truly tantalizing glimpse of another astonishing feature, a hint, a mere suggestion, a ghostly outline of the massive ridge near the moon's equator. It wasn't a clear resolved image of the ridge itself, but rather an indication, a slight distortion in the moon's limb, a subtle shadow or contour that spoke of something extraordinary. It was like catching a momentary flash of something extraordinary out of the corner of your eye, enough to know it was there, a significant structure, but not enough to fully comprehend its scale, its precise form, or its profound significance. The dawning realization began to settle, and Iapetus held even more secrets than initially imagined. A true prelude to revelation, a cosmic whisper hinting at a deeper, more profound weirdness yet to be unveiled. The stage was being set not for closure, but for a grander, more detailed exploration. The full picture, The breathtaking, almost impossible weirdness of Iapetus, its dramatic two-toned surface, its peculiar shape, and its impossible towering mountain range would have to wait. It would wait for the arrival of a dedicated Saturn explorer, a mission specifically designed not just to fly by, but to linger to orbit, to observe with sustained focus, and to truly unveil the secrets of this ringed world and its complex, diverse family of moons. And so, with the fleeting glimpses from Voyager, the cosmic anticipation for Iapetus only intensified, setting the stage for the next most crucial chapter in its quiet unfolding story. The universe, in its infinite patience, was preparing to lift another corner of its veil, revealing more of its intricate design. Enter the Cassini spacecraft, a magnificent feat of human engineering and scientific ambition, named fittingly after the moon's discoverer, Giovanni Domenico Cassini, the very same individual who first deduced Iapetus's two-faced nature centuries before. This dedication, etched into the very name of the probe, symbolized a full-circle journey of discovery, a return to the mysteries first glimpsed by an inquisitive mind centuries ago. Arriving at Saturn in 2004, after a long and deliberate journey across the vast expanse of the inner solar system, the Cassini mission would embark on an unprecedented undertaking. It would spend an astounding 13 years unveiling the secrets of the ringed planet and its diverse, often astonishing family of moons. It wasn't a quick flyby. It was a sustained, intimate exploration, an orbital residency designed to yield insights that fleeting glances could never provide. Iapetus, that elusive, enigmatic moon, was high on Cassini's list of targets. Its long-standing mysteries, its two-toned appearance, and the hints of an equatorial ridge made it a scientific priority. A jewel in Saturn's crown, begging to be understood. Cassini's observations, particularly a close targeted flyby in September 2007, truly transformed our perception of this distant world. During this crucial encounter, the probe swooped within an astonishingly close distance of just 1,640 kilometers of Iapetus's surface. To put that into perspective, that's roughly the distance from London to Rome or from New York City to Miami. Imagine sailing over the surface of a world at that proximity, the details rushing into view, previously hidden landscapes suddenly laid bare. This close encounter was a game-changer. It transformed Iapetus from a distant glint, a mere puzzle in the sky, into a complex world we could finally study in intricate detail. The images and data streamed back to Earth, revealing a topographical richness, a geological history, and surface characteristics that far exceeded anything previously imagined. It was as if a hazy dream had suddenly sharpened into a vivid reality, allowing scientists to pore over its features with a precision previously reserved for our own moon. The long wait was over. The mysteries that had patiently brewed for centuries were finally within reach of modern scientific scrutiny, and the answers in their quiet unfolding would prove to be even more extraordinary than the questions themselves. The veil, that cosmic illusion, was finally beginning to lift, piece by painstaking piece. Now that we have truly arrived at Iapetus, brought close by the diligent work of the Cassini spacecraft, let us begin to unravel its physical tapestry, to paint a portrait of this extraordinary moon based on the wealth of data that flowed back to Earth. One of the very first things Cassini's sophisticated instruments told us about Iapetus, a fundamental piece of its identity, concerned its inner whisper, its density and composition. Through careful measurements of its gravitational pull on the spacecraft, scientists were able to calculate its density, which proved to be remarkably low, just 1.22 times the density of water. This seemingly simple number holds a profound implication. It suggests strongly that Iapetus is composed of up to 75% water ice. Imagine that for a moment. A world largely made of frozen water, a giant ancient ice ball drifting through the vast cold emptiness of space. It's not a solid rock like our moon, nor a metallic core wrapped in stone. Instead, it's a colossal sphere of ice, perhaps, with a small rocky core nestled deep within its frozen heart. This composition immediately sets it apart from many other celestial bodies and tells us a great deal about its formation and the materials that were available in its birthplace, the frigid outer reaches of the early solar system. In a region where volatile compounds like water ice could condense and persist, Iapetus accreted from these abundant icy building blocks. This characteristic makes it a unique entity, a true frozen marvel contrasting sharply with the denser, more rocky or metallic bodies closer to the Sun. Its very makeup hints at the different cosmic recipes that yield the incredible diversity of worlds we find in our solar system. Beyond its icy heart, Cassini's observations also revealed a most peculiar exterior. Moving us from general composition to specific form, Iapetus does not possess a perfectly spherical shape. Instead, it has a distinctively oblate, walnut-like appearance. Imagine trying to sculpt a perfect sphere out of soft clay and then gently, almost imperceptibly, pressing down on its poles while allowing its middle to bulge slightly. That's a crude, earthbound analogy for an effect sculpted by cosmic forces. This non-spherical shape is directly, inextricably linked to the towering equatorial ridge that we will explore in more detail later. This ridge, acting like a structural girdle, prevents the Moon from settling into a perfectly round form under its own gravity, giving it that characteristic, almost squashed, unique outline. Visualizing this cosmic nut, a singular form in the solar system, immediately tells us that something extraordinary has happened here, something that has profoundly affected its very architecture. It's a shape that whispers of a dynamic, perhaps violent past, a past where forces were at play that sculpted its very silhouette. This peculiar outline is not just a cosmetic detail. It's a profound clue, an interplay of its internal composition, its rotational history, and the gravitational forces that have acted upon it over eons, all combining to produce a celestial body unlike almost any other. And while Iapetus holds a significant amount of water in its frozen state, the data from Cassini provided strong indications about the lack of one particular feature that has captivated our imagination on other moons. It likely doesn't possess a subsurface ocean like some of its more geologically active cousins, such as Enceladus or Europa. On those other fascinating worlds, scientists have found compelling evidence of vast liquid water oceans hidden beneath their icy shells, kept warm by the immense tidal heating generated by their primary planets. But for Iapetus, there's no evidence of recent geological activity. No plumes of water vapor erupting into space. No telltale cracks or resurfacing patterns on its ancient crust. Nor is there the consistent, strong tidal heating needed to maintain liquid water deep beneath its icy shell over billions of years. This paints a picture of a world frozen solid to its core, a deep, ancient cold permeating its very being. This absence of a subsurface ocean carries significant implications, especially for the tantalizing question of potential habitability and the search for life beyond Earth. While worlds with internal oceans offer exciting possibilities for liquid water environments and potential biological activity, Iapetus stands as a different kind of frozen wonder. It is a testament to a distinct evolutionary path, a world where the conditions simply did not allow for the persistent warmth and fluidity required for such hidden seas. It's a stark contrast with other ocean worlds, making Iapetus a unique, frozen testament to the sheer diversity of planetary environments within our own solar system. Its icy heart is not a dynamic, ever-changing liquid, but a static, solid monument to cosmic frigidity. And lastly, as we complete this physical portrait of Iapetus, let us consider its face, its outermost layer, the skin of this peculiar moon. Cassini's detailed images revealed a surface that is profoundly ancient cold and heavily cratered, particularly in the bright regions known as Ronterra. Imagine a venerable elder, its face etched with the lines of countless years, each mark a story of time passing. These craters, ranging in size from tiny pockmarks to vast basin-sized scars, are testimony to billions of years of bombardment. They are cosmic bullet holes, left by countless meteoroids and comets that have slammed into Iapetus's unyielding surface over eons. Each impact, a violent whisper of a distant event, contributes to a rich, complex history, a story of the early solar system's chaotic formative period. The preservation of these myriad features, these scars of cosmic history, is largely due to the very characteristic we just discussed, the lack of significant geological activity. Without volcanism, tectonic plates, or cryovolcanism to erase or resurface its outer layers, Iapetus's crust has remained largely undisturbed, acting as a profound, frozen ledger. It's like a cosmic archaeological site, where every layer, every crater, every ancient crack holds a record of the past, preserved in the deep freeze of space. By studying these craters, their sizes, their distribution, their degradation, scientists can piece together a timeline of impacts, reading the history of the solar system inscribed on Iapetus's enduring ancient face. It is a world that has silently witnessed the cosmic ages bearing the marks of that long silent vigil. Having explored the physical makeup of Iapetus, its icy composition, unique walnut shape, and ancient cratered face, let us now turn our gaze to its graceful yet unusual orbit. Picture, if you will, a slow, deliberate waltz in the vast cosmic ballroom, a dance that sets Iapetus apart from its more conventional siblings. Most of Saturn's major moons, like a well-drilled celestial chorus, tend to orbit in a relatively flat plane close to the planet's equator, where its majestic rings reside. They are like beads strung on a shimmering invisible thread, orbiting in harmonious unison. But Iapetus is different. It performs its dance much farther out, almost like a solitary dancer, on the fringes of the ballroom, setting its own unique rhythm. Its average distance from Saturn is about 3.5 million kilometers, an immense gulf of space that immediately hints at its distinctive nature. To put that into perspective, that's more than twice the distance of Titan, Saturn's largest and most famous moon, which orbits at a mere 1.2 million kilometers. This vast separation means Iapetus takes a considerable amount of time to complete just one full circuit around its giant primary. Its orbital period, its year in cosmic terms, stretches to a leisurely 79.3 Earth days. Imagine a world where a single day-night cycle, thanks to its tidal locking, perfectly matches its year. The sun would rise incredibly slowly, creeping across the sky for weeks on end, casting long, unchanging shadows that stretch like ancient fingers across its surface. And then it would just as slowly set, ushering in weeks of profound darkness. This slow, deliberate rotation has a profound impact on its surface processes and thermal dynamics, influencing how sunlight interacts with its peculiar, two-toned surface. It is a world where time seems to unfold at a different pace, a cosmic pendulum swinging with immense, unhurried grace. This significant distance, this cosmic isolation, dictates Iapetus's relationship with Saturn and its environment in profound ways. Because it orbits so far out, Iapetus is less affected by Saturn's magnetosphere and the intense radiation belts that envelop the inner moons. These belts, churning with energetic charged particles trapped by Saturn's powerful magnetic field, can bombard the surfaces of closer moons, altering their chemistry and eroding their fragile skins. But Iapetus, in its distant ballet, largely escapes this fierce cosmic weather. It's like standing far from a raging storm. You feel its distant rumble, but not its direct fury. This exposure to the raw, unfiltered power of the solar wind and cosmic rays unshielded by Saturn's magnetic bubble could very well have played a subtle, long-term role in shaping its surface chemistry and appearance over billions of years, adding another layer to its complex story. It is a world facing the unshielded cosmos, bearing the silent cumulative marks of that relentless exposure. Crucially, Iapetus's orbit is also slightly inclined tilted by about 15 degrees relative to Saturn's equatorial plane. Picture a flat spinning dinner plate representing Saturn's equator, where most of its major moons and rings dutifully orbit. Now imagine a tiny marble rolling around the edge of that plate, but its path isn't perfectly flat. It gently rises above the plate on one side and dips below on the other at an angle. That's Iapetus. This seemingly small tilt is a profound clue, a whispered hint about its formation or early migration history. Most of Saturn's closer, regular moons are thought to have formed within the same flattened disk of gas and dust that eventually coalesced to form Saturn itself and its rings orbiting neatly within that plane. But Iapetus's inclination suggests it might not have formed in the same way, or at least, not in the same precise location. Perhaps it formed much farther out beyond the main planetary disk. Or perhaps it was a captured body pulled into Saturn's gravitational embrace much later in the solar system's history. Its tilted path could be an echo of a different origin story, a cosmic outlier in its orbital dance forever hinting at a more complex, less straightforward beginning than its more orderly siblings. This deviation from the norm, this gentle tilt, is not just a detail for astronomers. It's a profound question etched into the very fabric of its motion, inviting us to contemplate the chaotic formative years of our solar system when giant planets migrated and rogue bodies were captured, reshaping the cosmic neighborhood in ways we are only just beginning to understand. Iapetus's orbit, then, is not just a predictable path, but a silent testament to a grand ancient drama of formation and evolution. But let us now turn our gaze to the most visually striking aspect of Iapetus, the very feature that captivated Cassini and continues to fill us with wonder, its surface, a canvas of profound and breathtaking contrasts. Iapetus is cleanly divided into two distinct regions, a cosmic yin and yang, a world quite literally split down the middle by an invisible yet intensely visible line. Imagine seeing this world up close, floating beside it, and witnessing this astonishing dichotomy with your own eyes. First, consider the leading hemisphere, the side that perpetually faces forward, as Iapetus carves its long solitary path around Saturn. This region is known as Cassini Regio, aptly named after the astronomer who first inferred its existence, and it is quite simply incredibly dark. Picture a patch of freshly laid asphalt on a moonless night, or the deepest, most absorbing black of coal dust. That's the visual impression. Cassini Regio covers about 40% of Iapetus's entire surface, a vast expanse of profound shadow. Its albedo, which is the scientific measure of how much light a surface reflects, is extremely low, somewhere between 0.03 and 0.1. This means it absorbs almost all the light that falls upon it, like a cosmic sponge soaking up photons. Sunlight, which travels billions of miles to reach this distant moon, strikes Cassini Regio and simply vanishes, consumed by its mysterious dark material. It is a realm of deep reddish browns, or even an almost absolute black, a silent, light-devouring expanse that truly justifies the moon's ancient reputation for vanishing. In stark, almost impossible contrast, there is the other side, the trailing hemisphere. This is the side that faces away from the direction of Iapetus's orbit, along with the moon's polar regions. This area encompasses majestic stretches of terrain like Monavu Terra to the north and Saragossa Terra to the south. And this region is incredibly bright. Imagine, if you can, the pristine brilliance of freshly fallen snow on a sunlit winter's day, or the dazzling pure white of brilliant water ice. That is the light reflected from this side of Iapetus. This part of the moon boasts an albedo of 0.5 to 0.6, meaning it reflects between 50% and 60% of the sunlight that strikes it. It shines with an almost ethereal glow, a beacon in the cold vacuum. This stark difference, this almost tenfold contrast in albedo, is not merely remarkable. It is the greatest interhemispheric albedo contrast that we know of in the entire solar system. Think about that for a moment. No other world, no other moon, no other planet exhibits such a dramatic fundamental division of light and shadow across its surface. It's a truly unique characteristic a profound visual statement from the cosmos. Imagine seeing this world up close, perhaps from the vantage point of a spacecraft slowly orbiting beside it. One side, a deep, absorbing reddish-brown or black, a realm of perpetual twilight, absorbing warmth and light. The other side, a dazzling, almost blinding white, reflecting coolness and brilliance back into the void. It's a world literally split down the middle, a cosmic masterpiece of duality. The boundary between these two halves is itself a subject of fascination. In some areas, particularly near the equator, where the contrast is most dramatic, the line separating the dark Cassini Regio from the bright trailing hemisphere can appear remarkably sharp, almost as if painted on with a giant cosmic brush. It's a crisp, clear delineation, an abrupt transition from profound darkness to brilliant light, as if two different worlds were seamlessly stitched together along a precise seam. This sharpness adds to the mystery, suggesting a process that is not gradual or diffuse, but rather distinct and efficient in its separation. However, in other areas, especially at higher latitudes, the transition is more gradual, more nuanced, offering subtle clues to the ongoing processes that sculpt this world. Here you might find bright rayed craters splattered across the dark terrain like scattered jewels or splashes of milk on a dark canvas. These are younger impact sites where the force of the collision has excavated the bright icy material from beneath the dark veneer, revealing the pure, pristine ice below. Conversely, you might also observe dark streaks dusting the bright terrain like splashes of mud on freshly fallen snow. These streaks are often associated with the dark material that has migrated or been deposited onto the bright regions, a testament to the dynamic interplay between the two halves. This interplay, this delicate dance of light and shadow, is vividly shown in the images returned by Cassini, which truly brought this alien world to life. They present a clear, undeniable vision of a world literally split down the middle, a cosmic canvas illustrating the profound power of natural processes to create beauty, wonder, and enduring mystery. The two-tone surface of Iapetus is not just a visual curiosity. It is a fundamental characteristic that speaks volumes about its history, its environment, and the subtle yet powerful forces that have shaped it over billions of years. It is a silent invitation to delve deeper to understand the unseen mechanisms that have painted such a striking portrait in the cold, distant reaches of our solar system. So what causes this profound yin-yang appearance, this almost impossible division of light and darkness on the face of Iapetus? For a long time, the leading theories proposed an internal origin, whispers of processes occurring deep within the moon itself. Perhaps some theorized there was some form of dark cryovolcanic material erupting from Iapetus's interior, slowly welling up and coating one side of the moon, much like terrestrial volcanoes spew lava onto Earth's surface. Imagine a slow geological seep, a dark, viscous substance oozing from cracks and fissures, gradually spreading across one hemisphere, leaving the other untouched. A paper reviewing the early Voyager data from Bradford Smith and his colleagues in 1981, seeing the initial low-resolution images, argued for this very theory. They identified certain ring shapes and features as potential evidence, suggesting they were craters, partially flooded with this dark eruptive material, lending weight to the idea that Iapetus was actively painting itself from within. However, as is often the case in the grand journey of scientific discovery, new data brings new perspectives and sometimes entirely new answers. The arrival of the Cassini spacecraft, with its vastly superior instruments and its unprecedented close-up views, began to gently yet firmly dismantle this elegant internal theory. Cassini's radar and imaging data revealed a crucial detail. The dark material on Iapetus forms a remarkably thin layer. Imagine a delicate dusting, perhaps only tens of centimeters to a meter thick in most places. It wasn't a deep foundational layer, as one might expect from widespread volcanic flows. Instead, it was more like a fragile veneer, a superficial coating. Furthermore, Another compelling piece of evidence emerged from the numerous impact craters within Cassini Regio, that dark, enigmatic expanse. These craters often excavated bright, icy material from underneath, like a punch through a thin, dark crust, revealing the pristine, brilliant ice below. This strongly suggested that the dark stuff wasn't welling up from below, originating from Iapetus's deep interior. Rather, it indicated that it was being deposited from above a gentle, steady rain of dark particles settling onto the moon's surface. The idea of an internal origin, while once compelling, began to recede like a fading dream, replaced by a more nuanced external explanation. With the internal origin theory gently set aside, scientists began to look outwards, beyond Iapetus itself, searching for culprits within the broader Saturnian system. And here, a fascinating piece of evidence from 1982 came into play. Spectrophotometric observations of the dark leading surface were made essentially analyzing the way the dark material reflected and absorbed light across different wavelengths. What they found was truly intriguing. The composition of this dark material was carbonaceous, meaning it contained a significant amount of carbon, and it bore a remarkable similarity to a very specific type of extraterrestrial material, that of the Murchison C2 meteorite, which famously fell to Earth during a shower in 1969. Imagine that. A tiny piece of a moon billions of miles away, showing the spectral fingerprint of a meteorite that landed right here on our planet. This similarity immediately pointed to a common origin, suggesting the dark material wasn't some unique exotic substance from Iapetus's core, but rather something more akin to primal, carbon-rich space dust. To explain this finding, the authors of that paper and subsequent researchers looked to potential culprits close to Iapetus, yet still within the sprawling gravitational embrace of the Saturn system. And a prime suspect emerged waiting patiently in the outer reaches Phoebe. Phoebe is a relatively large dark moon, quite distinct from Saturn's other more regular satellites. It holds a unique and somewhat rebellious position in the Saturnian family. Unlike most of Saturn's moons, which orbit in the same direction as the planet's rotation, Phoebe orbits the planet in the wrong direction, a retrograde orbit. And it does so at a great distance, far from the bustling inner moon system. This retrograde orbit is a crucial detail, a cosmic fingerprint hinting at its history. Scientists believe Phoebe was not born alongside Saturn from the same swirling disk of gas and dust. Instead, it was likely a captured body, a cosmic wanderer from the outer solar system, perhaps even from the distant Kuiper belt, snagged by Saturn's immense gravity long ago, over billions of years as Phoebe and other small dark retrograde moons. Like it continued their solitary backward dance, they have been subjected to countless impacts. Imagine a relentless bombardment of micrometeoroids, like tiny cosmic grains of sand, constantly peppering their surfaces. Each impact, however small, would gently, almost imperceptibly, kick up a fine dust. Over astronomical timescales, these myriad impacts have created a vast, tenuous ring of dark dust particles, stretching far beyond Saturn's main rings. It's not a dense, visible ring, like the famous AB or C rings. Rather, it's a diffuse, almost ghostly halo of fine, dark, cosmic grit. But where do these dust particles go once they're liberated from Phoebe's surface? This is where a subtle yet powerful cosmic mechanism comes into play, the Poynting-Robertson effect. Imagine a tiny speck of dust floating in the vastness of space. As sunlight composed of countless photons strikes this dust particle, it exerts a tiny amount of pressure. This is known as radiation pressure, a gentle push from the star. However, because the dust particle is also moving, it experiences a slight drag from the incoming photons, a bit like feeling a slight headwind. This drag, though incredibly subtle, causes the dust particle to slowly, inexorably spiral inwards towards the Sun. In the context of Saturn's system, this means the dust particles, having been liberated from Phoebe and other retrograde moons, gradually spiral inwards towards Saturn itself. And critically, as they spiral inwards, they continue to move in a retrograde direction, maintaining the backward motion they inherited from their parent bodies. This sets the stage for a cosmic encounter. Now let's bring our enigmatic moon Iapetus back into the picture and observe its dance in light of this incoming stream of dark dust. Iapetus, unlike Phoebe, orbits Saturn in a prograde direction, the same direction as Saturn's rotation and the vast majority of its other major moons. It's part of the main orderly celestial procession. However, as we discussed, its orbit is significantly farther out than the main rings and the closer bustling moons, placing it precisely in the path of this spiraling retrograde dust. As Iapetus journeys around Saturn, diligently following its prograde orbit, its leading hemisphere, the side that perpetually faces forward, much like the front of a car, essentially plows head-on into this incoming stream of retrograde dark particles. Imagine driving your car through a vast silent swarm of extremely fine, almost invisible insects. What happens? They mostly splatter on your front windshield, accumulating there, coating it in a fine dark film. That's precisely what happens to Iapetus. Its leading hemisphere acts like a giant cosmic windshield, constantly encountering and accumulating the fine carbonaceous dust particles originating largely from the Phoebe group. These particles moving against Iapetus's direction of travel impact and stick, gradually building up a thin dark veneer. The trailing hemisphere, on the other hand, is shielded by the moon itself. Like the back window of that car, it collects far less of this dark material, remaining relatively pristine and untouched by the relentless cosmic drizzle. This beautifully explains the initial deposition and why one side of Iapetus became dark while the other remained bright. But deposition alone, this constant gentle raining down of dark dust, doesn't fully explain the intensity of darkness we see on the leading side of Iapetus. The darkness is too profound, too absolute, for a mere thin layer of accumulated dust. Nor does it fully explain the remarkable sharpness and complexity of the border between the dark and bright regions, which, as we observed, can appear almost painted on. This is where a more intricate dynamic process comes into play, a cosmic feedback loop that amplifies the initial deposition and sculpts the moon's surface with incredible precision. This is where thermal segregation and water-ice sublimation enter the picture. Imagine that thin layer of dark material now coating the leading hemisphere of Iapetus. This dark material, because of its low albedo, absorbs significantly more sunlight than the surrounding bright ice. Even though Iapetus is incredibly cold, far from the warmth of the sun, this absorption causes the surface temperature of the dark regions to rise slightly, just enough to trigger a remarkable process. Even a small temperature increase, a whisper of warmth in the profound cold, is enough to cause the volatile water ice to sublimate. Sublimation is a fascinating process where a substance turns directly from a solid into a gas, bypassing the liquid phase entirely. Think of dry ice vanishing into a misty vapor. That's sublimation in action. On Iapetus, the water ice, warmed by the absorbed sunlight on the dark regions, turns directly into water vapor gas. This sublimating water vapor doesn't just disappear into the vastness of space without a trace, because Iapetus rotates very, very slowly. Its day is about 79 Earth days long, perfectly matching its orbital period. The daytime temperatures, however slight, their increase persist for an incredibly long time. This gives the ice plenty of time to sublimate away from the warmer dark areas. In fact, scientists have calculated that if Iapetus's surface were pure ice, the rate of sublimation would be so fast that we would see over 100 meters of ice lost to sublimation in 1 billion years. While this might seem slow, it's actually a significant rate for a celestial body in the outer solar system, faster than any other Saturnian satellite has experienced through this particular mechanism. So the ice is vanishing from the dark leading hemisphere. But where does it go? This is the elegant part of the process. The sublimated water vapor, now in a gaseous state, doesn't just dissipate randomly. Because Iapetus has a negligible atmosphere, these sublimating molecules follow ballistic trajectories like tiny silent projectiles launched from the surface. And here's the key: they preferentially recondense and freeze onto the coldest available surfaces. Which surfaces are these? They are naturally the already bright icy regions on the trailing hemisphere and near the poles. These areas reflect more sunlight, staying cooler, and thus act as cosmic cold traps, eagerly drawing in and refreezing the migrating water vapor. It's like a cosmic refrigeration system, with the cold, bright areas pulling moisture from the warmer, dark ones. This creates a powerful, self-reinforcing, runaway positive feedback loop. Imagine it like a subtle yet relentless cosmic dance of temperature and phase change. The dark areas coated with the carbonaceous dust get slightly warmer because they absorb more sunlight. This slight warmth causes their underlying ice to sublimate, turning into vapor. As the ice vanishes, the underlying dark dust concentrates, becoming even darker, absorbing even more heat and sublimating even more ice. It's a spiral into deeper darkness. Conversely, the bright areas already reflecting light and thus staying cold become even colder as they collect the migrating frost from the sublimating dark regions. They reflect even more sunlight, staying even colder, and thus become even more efficient at collecting more frost. It's a spiral into brighter brilliance. Over millions and billions of years, this elegant self-sustaining process has dramatically sharpened the boundary between the dark leading hemisphere and the bright trailing hemisphere, leading to the extreme, almost painted-on contrast we see today. The initial deposition of dust from Phoebe acts as the spark, the tiny catalyst, but the subsequent thermal segregation and ice sublimation are the powerful engines that drive the process to its remarkable conclusion. So the great dichotomy of Iapetus, its stunning two-toned appearance, seems to be a beautiful complex combination of external pollution from retrograde moons like Phoebe and an internal sorting mechanism driven by sunlight and the subtle yet persistent process of ice sublimation. It is a truly remarkable example of planetary processes at work, a testament to how seemingly small persistent forces acting over cosmic timescales can sculpt worlds in astonishing and unexpected ways, creating a masterpiece of light and shadow in the cold, distant reaches of our solar system. But the two-tone coloration, as stunning and perplexing as it is only part of Iapetus's strangeness. As Voyager 2 hinted at with its fleeting low-resolution glimpse, and as Cassini confirmed in breathtaking, undeniable detail, Iapetus possesses another truly unique feature in the known solar system, a colossal equatorial ridge. Imagine, if you will, not just a mountain, but a wall of mountains, stretching for an immense distance, encircling the very waist of this peculiar moon. This ridge is effectively a wall of mountains, a geological marvel unlike anything else we have thoroughly observed on a celestial body. It stretches for an astonishing 1,600 kilometers, which is roughly 1,000 miles. To put that into perspective, that's at least halfway around the moon's entire circumference, a massive unbroken barrier. Picture a seam running directly along the equator of a giant sphere, but instead of being flat, this seam is made of towering peaks and valleys. On average, this immense structure is about 200 kilometers wide at its base, a vast foundation supporting its monumental height, and it reaches towering heights of up to 20 kilometers above the surrounding terrain. To truly grasp the scale of this, consider that's significantly taller than Mount Everest, the highest peak on our own Earth. Everest, for all its majesty, reaches a little over 8.8 kilometers. Iapetus's ridge dwarfs it, more than doubling its height. It is a truly breathtaking edifice, a testament to geological forces on a scale we rarely comprehend. And the most baffling part, the detail that truly elevates this feature from merely remarkable to profoundly mysterious, is its location. It follows the equator almost perfectly. It's not a jagged random chain of mountains carved by ancient tectonics, like on Earth, or the chaotic result of a single colossal impact. Instead, it's a precise, unwavering line, a perfectly wrapped stony girdle, While primarily confined within the dark Cassini Regio, extending across that enigmatic dark hemisphere, there are tantalizing hints that more equatorial mountains identified by Voyager on the trailing hemisphere could be a continuation of this very structure. This suggests a singular globe-spanning event or process that shaped the entire moon. In images like the one taken by Cassini during its close flyby, the sheer scale of this feature is breathtaking. It immediately gives Iapetus a distinct walnut shape, as if the moon itself has been squeezed or formed around this central protruding band. You can almost feel the weight of this massive structure altering the very silhouette of the moon. What could have possibly formed this enormous belt of mountains? This is not a question with an easy answer. In fact, it remains one of the biggest ongoing mysteries of Iapetus, a silent, stony challenge to our understanding of planetary formation and evolution. It beckons us to ponder the very limits of what we imagine possible in the cosmic forge. The enigma of Iapetus's equatorial ridge has inspired several compelling hypotheses, each a fascinating attempt to explain this impossible structure, and each with its own unique strengths and subtle weaknesses. These ideas are like different lenses through which we try to peer into the moon's distant past, hoping to glimpse the event that sculpted this monumental feature. One leading idea, a particularly elegant and widely discussed hypothesis, suggests that the ridge is a relic of a much faster spinning past. Imagine Iapetus not as the slow, deliberate dancer it is today, but as a whirling dervish in its youth. Recent models carefully constructed by planetary scientists have suggested that very early in its history, perhaps shortly after its formation from the swirling cosmic dust and ice of the Saturnian nebula, Iapetus might have been rotating much, much more rapidly. Picture it spinning on its axis perhaps in as little as 16 hours a dizzying pace, compared to its current 79-day rotation. This rapid spin, like a child's top whirling incredibly fast, would have created immense centrifugal force, pushing material outwards away from the axis of rotation, much like water flung from a spinning clothes dryer. This force would have been strongest at the equator, causing the moon's equatorial regions to bulge outwards, creating a pronounced oblate shape. This would have occurred while the moon was still young and relatively plastic or partially molten, a pliable sphere of slushy ice and rock still warm from its formation, and the constant collisions that built it. In this soft, malleable state, the centrifugal forces could easily deform it, creating a prominent bulge around its middle. Then, as Iapetus cooled and solidified, slowly freezing solid from its outer layers inwards, this equatorial bulge would have become frozen in place. It would have been locked into the moon's rigid structure, an indelible mark of its rapid youth. Later, over millions and billions of years, the relentless pull of Saturn's gravitational interactions began its slow, inexorable work, acting like a cosmic brake. These tidal forces gradually slowed the moon's rotation down over vast stretches of time, gently tugging at Iapetus until it eventually became tidally locked to Saturn, reaching its current stately pace of rotating only once per orbit. That 79-day-long day we discussed. As its rotation slowed, the immense centrifugal force that had supported the bulge diminished. The outward push lessened. But because Iapetus was now a solid, rigid body, its crust couldn't fully relax back into a perfect sphere. The material, once supported by the rapid spin, essentially slumped downwards, no longer perfectly balanced by the centrifugal force. This slumping material, unable to flatten out completely, would have piled up near the equator, forming the massive linear ridge we see today. It's like a soft pillow that has been pushed into a shape and then allowed to harden. Even when the pressure is released, the form remains. This theory fits remarkably well with several key observations. Its perfect equatorial location is a natural consequence of a past rapid spin. Furthermore, the ridge's ancient, heavily cratered appearance strongly suggests it formed very early on in Iapetus's history, in its dynamic youth, rather than being a recent geological feature. It's a fossilized relic, a memory of a distant, faster past. However, for this theory to work, Iapetus would have had to spin incredibly fast, possibly even close to its structural breakup speed, the point where centrifugal forces might rip it apart, and it would have had to solidify while maintaining that pronounced bulge, a delicate dance between cooling and dynamic forces. While compelling these conditions push the boundaries of our understanding of moon formation, another intriguing hypothesis proposes a completely different origin for the ridge, looking not to Iapetus's internal dynamics, but to an external source, specifically the collapse of a subsatellite or a ring system that once orbited Iapetus itself. Imagine for a moment that Iapetus wasn't always alone. What if early in its history, perhaps after a giant impact on Iapetus itself or the capture of a smaller body, it temporarily possessed its own miniature debris ring? This ring, composed of countless icy and rocky fragments, would naturally orbit above its equator. Just as Saturn's rings orbit Saturn, the mechanism here is fascinating. If this miniature ring became unstable, perhaps due to subtle gravitational perturbations from Saturn, or if Iapetus itself migrated slightly in its orbit, the ring material may have been pushed just beyond the Roche limit. The Roche limit is a crucial concept in celestial mechanics. It's the point at which the tidal effects of a larger body, in this case, Iapetus, overwhelm the internal gravity of a smaller orbiting body, or even the internal cohesion of a ring. Inside the Roche limit, tidal forces would tear a moonlet apart. Outside it, a moonlet could form. But if material from a ring crossed back inside Iapetus's Roche limit, or if the ring itself became so unstable that its fragments could no longer sustain their orbits, then that material would no longer be able to maintain its stable orbital configuration. Instead, it would gradually, slowly begin to rain down onto the surface of Iapetus, drawn inexorably by the moon's own gravity. And critically, this material would pile up preferentially along the equator. Why the equator? Because of the principle of conservation of angular momentum. As the orbiting particles lost energy and spiraled inwards, they would tend to settle in the lowest gravitational potential well, which for a rotating body is the equator. This raining down of ring material accumulating over vast stretches of time could potentially form the massive linear ridge we observe today. This theory could also potentially explain why the ridge seems most prominent on the dark leading hemisphere if the ring material itself was dark, or if its deposition somehow coincided with the influx of dark dust from Phoebe, perhaps amplifying the thermal segregation process. Some models even suggest that the breakup of a small moonlet within Iapetus's Roche limit could provide enough material to form such a ridge, a quiet internal catastrophe, creating a grand external feature. While elegant in its explanation for the location of the ridge, the exact mechanisms for forming such a ring around a moon like Iapetus and then subsequently causing it to collapse in such a controlled manner are still debated among scientists. It requires a very specific set of circumstances and events in the distant past. It's a compelling idea, offering a different kind of cosmic drama, an internal ring system collapsing upon its parent body. Beyond these two leading hypotheses, other theories for the equatorial ridge have been proposed, though they often struggle to provide a complete explanation. For instance, ideas involving tectonic processes, the large-scale movement of a moon's crust, or convective upwelling from the interior, where warmer, less dense material rises from deep within, struggle to explain why such activity would be so narrowly confined to the equator over such a vast, continuous distance. On Earth, tectonic forces create mountain ranges, but they are typically more scattered and less perfectly linear than Iapetus's ridge. A giant impact is also highly unlikely to produce a long linear and perfectly equatorial feature. Impacts tend to create circular craters or chaotic irregular terrain, not a global mountain belt. Cassini's detailed images provided crucial insights into the ridge itself. They unequivocally show that the ridge is heavily cratered, a powerful confirmation of its ancient origins. This visual evidence strengthens the argument that whatever process formed it, it must have happened very early in Iapetus's history, perhaps within the first few 100 million years of the solar system's formation, when the cosmos was still a tumultuous, active place. The craters superimposed on the ridge serve as silent clocks indicating its immense age. The images also show that it appears to be structurally composed of icy crustal material, consistent with Iapetus's overall composition. Furthermore, some sections of the ridge show evidence of landslides and collapse features, indicating that over eons, gravity has gently reshaped its towering slopes, pulling down loosened material, forming debris fields at its base. Whatever the precise process that sculpted it, the equatorial ridge of Iapetus stands as a monumental memento of Iapetus's dynamic youth, a frozen record of primordial processes we are still striving to understand. It is a geological riddle, a grand silent question etched into the very surface of a distant moon, reminding us that even in our own cosmic backyard, there are wonders and mysteries that continue to defy simple explanation, inviting us to keep looking, keep pondering, and keep dreaming of the forces that shaped the worlds around us. It is a testament to the raw power of the early solar system, a fossilized echo of events long past, waiting for our minds to finally decode its ancient story. So what do we truly know about Iapetus after centuries of distant glances and the intimate embrace of the Cassini mission? Certainly more than we used to, far more than Cassini himself could have dreamed, but perhaps still less than we'd like for the universe. In its boundless generosity, always holds back a few secrets like a magician, with one last enchanting trick up their sleeve. The Cassini mission fundamentally changed our perception of this fascinating moon, forever transforming it from a mere point of light into a complex, captivating world. It was a cosmic detective patiently gathering clues over years, slowly piecing together the moon's intricate story. The close flyby, that pivotal moment in September 2007, when Cassini swooped within a mere 1,340 kilometers of Iapetus's surface, provided the crucial data that finally solidified the exogenic dust and sublimation theory for the planet's two faces. Before Cassini, this elegant explanation involving dust from Phoebe and the amplification of thermal processes was a compelling hypothesis, a beautiful idea that made sense. But with Cassini's direct observations, the detailed spectral readings, the high-resolution images showing the thinness of the dark layer, and the exposed ice beneath the craters, it moved from theory to near certainty. Imagine the quiet satisfaction of scientists seeing their models confirmed, witnessing the cosmic processes unfold before their very eyes, albeit through the proxy of a robotic probe billions of miles away. It turned a profound visual mystery into a scientifically understood, albeit still astonishing, phenomenon. The moon's vanishing act was no longer pure magic, but a complex natural interplay of cosmic dust and the thermodynamics of ice. Beyond the captivating two-tone surface, Cassini also gifted us with astonishing high-resolution views of the equatorial ridge. For centuries, this ridge was a blurry hint, a perplexing anomaly. Now, with Cassini's sharp, detailed images, we could finally study its structure and morphology with unprecedented clarity. We could see its towering heights, its immense width, the craters etched upon its ancient slopes, and even the subtle signs of past landslides. These images allowed geologists to pore over its features to understand its scale and to begin to piece together its internal composition. Even if its origin remains one of Iapetus's most enduring and beautiful debates, the ability to study it in such exquisite detail moved the conversation from pure speculation to informed scientific inquiry. It transformed the ridge from an enigma to a concrete, albeit still mysterious, geological feature that we could now truly grapple with. Furthermore, Cassini's sophisticated instruments went beyond mere imaging. They meticulously measured Iapetus's shape-gravity field and surface composition with unprecedented accuracy. Imagine sending a tiny, exquisitely sensitive scale and a complex chemical analyzer billions of miles away to weigh and analyze a distant world. That's what Cassini achieved. By precisely tracking the probe's minute deviations in orbit as it passed close to Iapetus, scientists could map the moon's gravitational field, which in turn allowed them to refine calculations of its internal structure and density distribution. Spectral instruments carefully analyzed the light reflected from different parts of its surface, providing detailed insights into the specific chemical makeup of the icy and dark materials. Each of these precise measurements was like a thread woven into a richer, more detailed tapestry of understanding, slowly painting a comprehensive portrait of this peculiar world. Without Cassini, Iapetus would have largely remained the faint, perplexing point of light it was. For centuries, a beautiful but inscrutable object in the night sky, its secrets locked away by distance and resolution. And yet, despite all these magnificent revelations, despite the leaps in our understanding, there are still so many mysteries that cling to Iapetus. Like the ancient ice on its bright hemisphere, the universe, in its infinite complexity, always holds more questions than answers, especially at the frontiers of our knowledge. Perhaps the most prominent lingering question, the one that continues to fuel scientific debate and imaginative speculation, is, what is the true origin of Iapetus's ridge? We have two compelling hypotheses: the faster spin theory and the collapsing ring theory, both of which offer elegant explanations for its equatorial location and immense scale. But which one is the right one? Or is it perhaps a combination of both? Or something entirely different, a process we haven't even conceived of yet? The evidence for each theory is strong, yet not definitive enough to entirely rule out the other. The heavily cratered surface of the ridge tells us its ancient formed very early, but it doesn't definitively tell us how it formed. Was Iapetus once spinning so fast that it almost ripped itself apart, leaving a fossilized bulge? Or did it once possess its own miniature ring system, a delicate halo of debris that eventually rained down upon its equator? These are profound questions about the very mechanics of planetary formation and evolution, questions that Iapetus holds close to its icy heart, waiting for perhaps a future mission or a breakthrough in theoretical understanding to provide a definitive answer. For now, the towering wall remains a silent, monumental enigma, a frozen echo of a violent, distant youth. Another profound question concerns the very material that creates Iapetus's peculiar dark face. What is the dark material of Iapetus's mysterious face actually composed of, beyond something simply carbonaceous? We know from spectral analysis that it's carbon-rich, similar to certain meteorites, but carbonaceous is a broad term. Is it some form of primordial organic goo, a complex mixture of simple hydrocarbons, or something even more exotic? Is it related to the building blocks of life, or simply the burnt remnants of ancient cosmic dust? The exact chemical composition could tell us so much about the conditions in the outer solar system during its formation and about the processes that act upon such materials over billions of years. Without a physical sample, without being able to run it through laboratories here on Earth, its precise chemical fingerprint remains somewhat blurred. It's like knowing a book is written in a certain language, but not being able to read the intricate words themselves, only inferring the general subject. The subtle variations in its spectral signature, the nuanced way it absorbs and reflects light, suggest a rich chemical complexity that we can only guess at from afar, unless we go there, unless humanity sends another dedicated mission, one perhaps designed not just to orbit and image, but to land, to collect samples, to truly touch and analyze the surface of Iapetus. It will be difficult to know for sure. The answers to these lingering questions require a level of intimacy and direct interaction that our current technology and our current mission plans do not yet provide. And here lies a bittersweet reality. As of now and for the foreseeable future, no missions are currently planned to sample or even circle this perplexing place. Iapetus, for all its wonders and all the knowledge it has already yielded, remains beyond the immediate reach of our robotic explorers. It will continue its slow, stately orbit around Saturn, forever turning its two faces to the distant sun, holding its colossal ridge as a silent monument to an ancient past. So, for now, we remain in the dark about many of its deepest secrets, a fitting irony perhaps given its dark hemisphere. After all, as we began this journey, Iapetus was once the ultimate vanishing act, a celestial magician defying explanation. And a magician, as the old saying goes, never truly reveals their secrets completely, always leaving a tantalizing thread of mystery to draw us back for another ponder. This quiet, enduring mystery is not a failure of science, but an invitation. It is an invitation to wonder, to stretch our imaginations, to continue asking the big questions that pull us out of the mundane and connect us to the vast, incomprehensible beauty of the cosmos. Iapetus, with its unique characteristics, its two-tone surface born of cosmic dust and subtle temperature shifts, and its impossible ancient ridge, serves as a powerful reminder of the incredible diversity and unexpected phenomena that await us in the universe. It reminds us that even in our own cosmic backyard, there are still worlds that hold profound, beautiful secrets, worlds that challenge our assumptions and expand the very boundaries of our understanding. Imagine the complex interplay of forces that must have unfolded over billions of years to sculpt such a world. The faint whisper of dust, carried by solar radiation across millions of kilometers, gently landing on a leading face. The subtle warmth of the sun, barely registering as heat to our senses, but enough to trigger the sublimation of ice, a process of planetary self-sculpture. The movement of water vapor across vast distances on a world with no atmosphere, condensing on colder, brighter regions, amplifying the contrast over eons. And then, the monumental enigma of the ridge itself, whether a frozen relic of a faster, more violent youth, or the ghostly remnants of a shattered ancient ring. Each element, a piece of a grand cosmic narrative unfolding silently, majestically in the cold vacuum. Iapetus stands as a testament to the fact that the universe is far more imaginative than we are. Our theories, no matter how elegant, are often just stepping stones to even grander, more complex realities. It pushes us to think beyond familiar geological processes, to consider the long, slow, inexorable work of subtle forces over unimaginable timescales. This moon, this vanishing act, forces us to embrace the beautiful uncertainty of discovery, to appreciate that the journey of asking questions is often as rewarding, if not more so, than the arrival at an answer. And so, as we conclude this quiet contemplation of Iapetus, let its enduring mysteries settle gently in your mind. Let the image of its two faces, one dark and absorbing the other, bright and reflecting, and its impossible encircling mountain, be a soothing backdrop to your thoughts. Allow yourself to drift on the currents of cosmic wonder, knowing that even in the vastness of space, there are places that whisper profound stories, stories of creation, transformation, and enduring enigma. These are the whispers that remind us of the universe's endless capacity for surprise, its boundless creativity, and its quiet invitation to keep looking up, keep pondering, and keep dreaming of what else might be out there waiting to be discovered. The cosmos is a lullaby of unanswered questions, and Iapetus sings one of the most enchanting verses. Now let us turn our attention fully to that monumental anomaly, that staggering geographical feature that sets Iapetus apart from almost every other known celestial body, the colossal equatorial ridge. As Voyager 2, with its fleeting distant pass, had only hinted at with a subtle distortion, Cassini, in its magnificent close-up views, confirmed its existence in breathtaking, undeniable detail. This wasn't merely a hint anymore. It was a grand, undeniable reality, a testament to forces we are only just beginning to comprehend. Imagine, if you will, not just a single mountain or a small chain of hills, but an entire wall of mountains, a continuous towering barrier that stretches for an immense distance, seemingly encircling the very waist of this peculiar moon. This ridge is quite simply a geological marvel, unlike almost anything else we have observed with such clarity on a celestial body in our solar system. It extends for an astonishing length of around 600 kilometers, which, to give you a sense of the scale, is roughly 1,000 miles. That's a significant portion of the moon's circumference, reaching at least halfway around its entire middle. Picture a perfectly straight seam running directly along the equator of a giant sphere, but instead of being flat or recessed, this seam is made of towering peaks and deep-shadowed valleys. On average, this immense structure boasts a formidable width of about 200 kilometers at its base. This is no narrow spine. It's a vast, expansive foundation supporting the monumental height that rises from it. And rise it does. This ridge reaches truly towering heights of up to 20 kilometers above the surrounding terrain. To truly grasp the sheer scale of this, let us bring it closer to home. Consider Mount Everest, the highest peak on our own Earth, a mountain that humbles even the most seasoned climbers. Everest, for all its majestic grandeur and formidable challenge, reaches a little over 8.8 kilometers above sea level. Iapetus's ridge dwarfs it more than doubling its height. It is an edifice so grand that it truly strains our terrestrial imagination, an alien mountain range on a scale that forces us to redefine what is possible in the cosmic landscape. It is a truly breathtaking structure, a silent, stony testament to geological forces of immense power unfolding on a scale we rarely comprehend. What makes this feature even more profoundly baffling, the detail that truly elevates this structure from merely remarkable to utterly mysterious, is its precise location and unwavering form. It follows the equator almost perfectly. It's not a jagged, haphazard chain of mountains, carved by random ancient tectonic shifts, like on Earth, or the chaotic asymmetrical result of a single colossal impact. Instead, it's a precise, unwavering line, a beautifully wrapped stony girdle, as if some cosmic artisan had meticulously placed it there. While it is primarily confined within the dark Cassini Regio, that enigmatic dark hemisphere we've discussed extending across that vast, light-absorbing expanse, there are tantalizing hints from earlier lower-resolution data that more equatorial mountains identified by Voyager on the trailing hemisphere could, in fact, be a continuation of this very structure. This suggests a singular globe-spanning event or process that shaped the entire moon, leaving its indelible mark across both its light and dark faces. In the images returned by Cassini, particularly those captured during that incredibly close flyby, the sheer scale of this feature is profoundly breathtaking. It doesn't just look like a bump on the surface, it visually alters the very silhouette of the moon. It immediately gives Iapetus a distinct walnut shape, as if the moon itself has been gently squeezed or formed around this central protruding band. You can almost feel the weight of this massive structure altering the very equilibrium of the moon, giving it an otherworldly, almost carved appearance. This unique profile is a constant reminder of the ridge's immense size and its fundamental influence on Iapetus's overall form. What cosmic event, what unimaginable force could have possibly formed this enormous belt of mountains? This is not a question with an easy, readily available answer. In fact, it remains one of the biggest ongoing mysteries of Iapetus, a silent, stony challenge to our understanding of planetary formation and evolution. It beckons us to ponder the very limits of what we imagine possible in the cosmic forge, forcing us to consider processes that might be alien to our Earth-centric geological experience. The ridge stands as a profound question mark etched into the face of a distant world, compelling us to consider ancient energies and transformations that shaped the earliest moments of our solar system. It is a silent, monumental enigma waiting for the right key to unlock its ancient story, the enigma of Iapetus's equatorial ridge, with its impossible scale and precise placement, has naturally inspired several compelling hypotheses, each a fascinating attempt to explain this unique structure. These ideas are like different lenses through which we try to peer into the moon's distant ancient past, hoping to glimpse the precise event or series of events that sculpted this monumental feature onto its surface. Each hypothesis offers a plausible pathway, yet each also faces its own set of subtle challenges and lingering questions, keeping the debate alive in the quiet halls of scientific inquiry. One leading idea, a particularly elegant and widely discussed hypothesis, suggests that the ridge is a relic of a much faster spinning past. Imagine Iapetus not as the slow, deliberate dancer it is today, perpetually keeping one face towards Saturn, but as a dynamic, almost furious whirligig in its youth. Recent models carefully constructed by planetary scientists using sophisticated computer simulations have suggested that very early in its history, perhaps shortly after its formation from the swirling cosmic dust and ice of the Saturnian nebula, Iapetus might have been rotating much more rapidly than it does now. Picture it spinning on its axis, perhaps as fast as once every 16 hours, a dizzying pace compared to its current stately rotation period of 79 Earth days. This rapid spin, much like a child's top whirling incredibly fast, would have created immense centrifugal force. This force is the outward push that you feel when you're on a merry-go-round, spinning very quickly, constantly trying to throw you off. Applied to a celestial body, this force pushes material outwards, away from the axis of rotation. Crucially, this outward push would have been strongest at the equator, where the rotational speed is highest. This intense centrifugal force would have caused the moon's equatorial regions to bulge outwards, creating a pronounced oblate shape, flattened at the poles and distended at the middle. This would have occurred while the moon was still young and relatively plastic, or even partially molten, a pliable sphere of slushy ice and rock, still retaining some residual heat from its formation and the constant energetic collisions that built it. In this soft, malleable state, the centrifugal forces could easily deform it, shaping it into an ellipsoid with a prominent bulge around its middle, much like a rapidly spinning pizza dough that flattens and wedges out at the edges. Then, as Iapetus began its long, slow process of cooling and solidifying, slowly freezing solid from its outer layers inwards, this newly formed equatorial bulge would have become frozen in place. It would have been locked into the moon's rigid, unyielding structure, an indelible fossilized mark of its rapid, energetic youth. But the story doesn't end there. Later, over immense spans of cosmic time, millions and even billions of years, the relentless pull of Saturn's gravitational interactions began its slow, inexorable work. These powerful tidal forces, the same forces that cause tides in our oceans, acted like a cosmic brake, subtly yet persistently tugging at Iapetus. This constant, gentle tug gradually slowed the moon's rotation down over vast stretches of time, bleeding off its rotational energy, until it eventually reached its current state, becoming tidally locked to Saturn. This means its rotation period perfectly matched its orbital period, reaching its stately pace of rotating only once per orbit. That 79-day-long day we discussed earlier. As its rotation slowed, the immense centrifugal force that had supported the bulge diminished. The outward push, which had sustained that equatorial swelling, gradually lessened. But because Iapetus was now a solid, rigid body, its solidified crust couldn't fully relax back into a perfect sphere. The material, once supported and held out by the rapid spin, essentially slumped downwards, no longer perfectly balanced by the centrifugal force. This slumping material, unable to flatten out completely and redistribute itself uniformly around the cooling, solidifying sphere, would have piled up preferentially near the equator, forming the massive linear ridge we see today. It's like a soft, pliable pillow that has been pushed into a specific shape and then allowed to harden. Even when the pressure is released, the form remains a permanent imprint. This theory fits remarkably well with several key observations. Its perfect equatorial location is a natural and direct consequence of a past rapid spin, as centrifugal forces are strongest and most effective at the equator. Furthermore, the ridge's ancient heavily cratered appearance strongly supports the idea that it formed very early on in Iapetus's history, in its dynamic turbulent youth, rather than being a more recent geological feature. It's a fossilized relic, a memory etched in stone of a distant faster past. However, for this theory to work, Iapetus would have had to spin at an incredibly fast rate, possibly even close to its structural breakup speed. The theoretical point where the centrifugal forces would be so strong that they might literally rip the moon apart. And it would have had to solidify, while maintaining that pronounced bulge, a delicate dance between cooling solidification and dynamic forces. While compelling these conditions push the boundaries of our current understanding of moon formation and internal dynamics, leaving a whisper of doubt. Another intriguing hypothesis proposes a completely different origin for the ridge, one that looks not to Iapetus's internal dynamics or primordial spin, but to an external source, specifically the collapse of a subsatellite or ring system that once orbited Iapetus itself. Imagine for a moment that Iapetus wasn't always the solitary moon we observe today. What if early in its history, perhaps after a colossal impact on Iapetus itself, that ejected a vast amount of debris, or perhaps the capture of a smaller body into its own gravitational embrace, it temporarily possessed its own miniature debris ring? This ring, composed of countless icy and rocky fragments, like a miniature version of Saturn's grand rings, would naturally orbit above Iapetus's equator. Drawn into that stable orbital plane by its rotation, the mechanism here is complex, yet fascinating. If this miniature ring system became unstable, perhaps due to subtle gravitational perturbations from Saturn, or if Iapetus itself migrated slightly in its orbit, altering the delicate balance of its internal ring, the material within that ring may have been pushed just beyond a critical boundary known as the Roche limit. The Roche limit is a crucial concept in celestial mechanics. It's the theoretical point at which the tidal effects of a larger body, in this specific case, Iapetus, overwhelm the internal gravity of a smaller orbiting body like a moonlet, or even the internal cohesion of a ring of particles. Inside the Roche limit, tidal forces are so strong they would tear a small moonlet apart. Outside it, a moonlet could potentially coalesce and remain intact. But in this scenario, if material from an existing ring crossed back inside Iapetus's Roche limit, or if the ring itself became so unstable that its individual fragments could no longer sustain their stable orbital configuration, then that material would no longer be able to maintain its delicate dance in orbit. Instead, it would gradually slowly begin to rain down onto the surface of Iapetus, drawn inexorably by the moon's own gravity. This descent would not be a sudden cataclysmic shower, but a slow, persistent fall, like cosmic snowflakes accumulating over vast stretches of time. And critically, this material would pile up preferentially along the equator. Why the equator? Because of the principle of conservation of angular momentum. As the orbiting particles lost energy and spiraled inwards, they would naturally tend to settle in the lowest gravitational potential well, which for a rotating body is the equator. Imagine particles losing energy and gradually descending. The most stable place for them to settle, where they can shed the most energy, is along the fattest part of the spinning body. This raining down of ring material accumulating over vast stretches of time could potentially form the massive linear ridge we observe today. This theory could also potentially explain why the ridge seems most prominent on the dark leading hemisphere if the ring material itself was dark, or if its deposition somehow coincided with the influx of dark dust from Phoebe, perhaps amplifying the thermal segregation process we discussed earlier. Some models even suggest that the breakup of a small moonlet within Iapetus's Roche limit, pulled apart by the moon's gravity, could provide enough material to form such a ridge, a quiet internal catastrophe for the moonlet, creating a grand external feature on Iapetus. While elegant in its explanation for the precise equatorial location of the ridge, the exact mechanisms for forming such a substantial ring around a moon like Iapetus and then subsequently causing it to collapse in such a controlled uniform manner are still debated among scientists. It requires a very specific and perhaps unlikely set of circumstances and events to have transpired in the distant chaotic past of the solar system. It's a compelling idea, offering a different kind of cosmic drama. An internal ring system collapsing upon its parent body, painting a new chapter in its story. Beyond these two leading hypotheses, which currently hold the most sway in scientific circles due to their ability to explain key observations, other theories for the equatorial ridge have been proposed. However, these often struggle to provide a complete and satisfying explanation for all of the ridge's characteristics, especially its precise linearity and immense uniform scale. For instance, ideas involving tectonic processes, the large-scale movement and deformation of a moon's crust similar to plate tectonics on Earth, or convective upwelling from the interior, where warmer, less dense material rises from deep within the moon, bringing energy and material to the surface, face significant hurdles. They struggle to explain why such activity would be so narrowly confined to the equator. Over such a vast, continuous distance, on Earth, tectonic forces create sprawling, complex mountain ranges, but they are typically more scattered, less perfectly linear, and rarely form such a precise global girdle as Iapetus's ridge. If there were internal heat and convection, one might expect more widespread surface features, not just a single precise band. Similarly, the idea of a giant impact creating the ridge is also highly unlikely to produce such a long linear and perfectly equatorial feature. While colossal impacts can certainly create massive geological structures, they typically result in circular craters or chaotic irregular terrain, scattering material radially, not neatly piling it up along a perfect line around the entire circumference of a moon. An impact would likely leave a much more asymmetrical scar, lacking the elegant precision of Iapetus's ridge. Cassini's detailed images provided crucial insights not just into the scale and location of the ridge, but also into its very nature. They unequivocally show that the ridge is heavily cratered, a powerful and undeniable confirmation of its ancient origins. This visual evidence, these countless pockmarks from billions of years of cosmic bombardment, strongly strengthens the argument that whatever process formed it, it must have happened very early in Iapetus's history, perhaps within the first few 100 million years of the solar system's formation, during a time when the cosmos was still a tumultuous active place, brimming with leftover debris and energetic collisions. The craters superimposed on the ridge serve as silent clocks indicating its immense age and showing that it has endured the test of time for eons. The images also reveal that the ridge appears to be structurally composed of icy crustal material, consistent with Iapetus's overall composition as a world primarily made of water ice. This tells us that it's not made of some exotic superdense rock, but rather the same basic building blocks as the rest of the moon, simply arranged in an extraordinary way. Furthermore, close inspection of some sections of the ridge shows compelling evidence of landslides and collapse features. These are the subtle scars left by gravity, doing its relentless work over eons, pulling down loosened material from the towering slopes, forming debris fields and smaller fan-shaped deposits at its base. These smaller scale features tell a story of gradual erosion and reshaping. Since its original formation, a quiet, ongoing process of modification over vast spans of time. Whatever the precise process that sculpted it, whether a rapidly solidifying, fast-spinning world, or the remnants of a shattered internal ring, or some other yet-to-be-conceived mechanism, the equatorial ridge of Iapetus stands as a monumental memento of Iapetus's dynamic youth, a frozen record of primordial processes we are still striving to understand. It is a geological riddle, a grand silent question etched into the very surface of a distant moon, reminding us that even in our own cosmic backyard, there are wonders and mysteries that continue to defy simple explanation, inviting us to keep looking, keep pondering, and keep dreaming of the profound ancient forces that shaped the worlds around us. It is a testament to the raw, untamed power of the early solar system, a fossilized echo of events long past waiting for our minds to finally decode its ancient story, a quiet challenge in the boundless canvas of space. So what do we truly know about Iapetus, this extraordinary two-faced world, after centuries of distant glances and the intimate embrace of the Cassini mission? The answer, as is often the case in the grand journey of scientific discovery, is nuanced. More than we used to, certainly far more than Giovanni Domenico Cassini himself could have dreamed in his 17th century observatory, yet perhaps still less than we'd like for the universe, in its boundless generosity, always holds back a few secrets, like a cosmic magician with one last enchanting trick up their sleeve. The Cassini mission, a monumental endeavor of international collaboration and scientific ingenuity, fundamentally and irrevocably changed our perception of this fascinating moon, forever transforming it from a mere point of light, a curious anomaly, into a complex, captivating world, rich with its own unique history and geological wonders. It was, in essence, a tireless cosmic detective patiently gathering clues over many years, slowly, meticulously piecing together the moon's intricate, enigmatic story. The close flyby, that pivotal moment in September 2007 when Cassini swooped within a mere 1,640 kilometers of Iapetus's surface, was a truly transformative event. This close encounter provided the crucial definitive data that finally solidified the exogenic dust and sublimation theory for the moon's two faces. Before Cassini, this elegant explanation involving the steady, gentle rain of carbonaceous dust from the distant moon, Phoebe, and the subsequent amplification of thermal processes on Iapetus's surface was a compelling hypothesis. It was a beautiful idea, a logical construct that made intuitive sense, tying together disparate observations into a coherent narrative. But with Cassini's direct high-resolution observations, the detailed spectral readings that identified the dark material's composition, the sharp images showing the astonishing thinness of the dark layer, and the visible pristine ice exposed beneath the countless craters, the theory moved from a compelling idea to near certainty. Imagine the quiet satisfaction that must have filled the control rooms and scientific centers on Earth as these data streamed in, confirming centuries-old deductions and modern hypotheses. It was the thrill of seeing scientific models confirmed, witnessing the cosmic processes unfold before our very eyes, albeit through the proxy of a robotic probe sailing billions of miles away. It was a profound moment of intellectual validation. This data meant that Iapetus's peculiar two-toned surface, its dramatic visual dichotomy, was no longer pure magic, no longer an inscrutable trick of the light, but a complex natural interplay of external cosmic dust and the fundamental thermodynamics of ice. The moon's vanishing act, once a source of deep bewilderment, was revealed to be a beautiful, intricate dance between light-shadow and the subtle, persistent work of sublimation. Beyond the captivating and now largely understood two-toned surface, Cassini also gifted us with astonishing high-resolution views of the equatorial ridge. For centuries, this colossal structure was a blurry hint, a perplexing anomaly, a whisper of a possibility in the distant images from Voyager. Now, with Cassini's sharp, detailed images captured from unparalleled proximity, we could finally study its structure and morphology with unprecedented clarity. The images revealed its truly towering heights, its immense width, the countless craters etched upon its ancient slopes, silent witnesses to billions of years of cosmic history, and even the subtle, delicate signs of past landslides where material had slumped down its slopes under gravity's persistent pull. These detailed images allowed geologists and planetary scientists to pore over its features with a level of precision previously unimaginable. They could measure its dimensions, map its contours, understand its incredible scale, and begin to piece together its internal composition, from the way it behaved gravitationally. Even if its origin remains one of Iapetus's most enduring and beautiful debates, a testament to the universe's endless capacity for surprise, the ability to study it in such exquisite detail moved the conversation from pure unbridled speculation to informed scientific inquiry. It transformed the ridge from a mere enigma into a concrete, albeit still mysterious geological feature that we could now truly grapple with, feeding our models and pushing the boundaries of our understanding of how such colossal structures could form on a celestial body. It was as if a veiled statue had suddenly been revealed, allowing us to admire its form even if the sculptor remained unknown. Furthermore, Cassini's sophisticated suite of instruments went far beyond mere imaging. It meticulously measured Iapetus's shape, its gravity field, and its surface composition with unprecedented accuracy. Imagine, if you will, the extraordinary feat of engineering and science involved in sending a tiny, exquisitely sensitive scale and a complex chemical analyzer billions of miles away, equipping them to precisely weigh and analyze a distant world without ever physically touching it. That's precisely what Cassini achieved. By precisely tracking the probe's minute deviations in its orbit as it passed close to Iapetus, scientists could map the moon's gravitational field with incredible fidelity. This gravitational map, in turn, allowed them to refine their calculations of its internal structure, its density distribution, and the very way its mass was arranged beneath its surface. Spectral instruments on board carefully analyzed the sunlight reflected from different parts of Iapetus's surface. By breaking down this reflected light into its constituent wavelengths, they provided detailed insights into the specific chemical makeup of the icy and dark materials, revealing not just that it was ice or carbonaceous, but beginning to hint at the types of ice and the specific organic compounds present. Each of these precise measurements, each data point meticulously collected and transmitted across the vast cosmic distances, was like a thread woven into a richer, more detailed tapestry of understanding, slowly, patiently painting a comprehensive portrait of this peculiar world. Without Cassini, Iapetus would have largely remained the faint, perplexing point of light. It was for centuries a beautiful but ultimately inscrutable object in the night sky, its deepest secrets locked away by distance and the limitations of earthbound observation. Cassini was the key that unlocked these secrets, turning ancient wonder into modern insight. And yet, despite all these magnificent revelations, despite the monumental leaps in our understanding that Cassini provided, there are still so many mysteries that cling to Iapetus, like the ancient pristine ice on its bright hemisphere. The universe, in its infinite complexity and its profound, elegant design, always holds more questions than answers, especially at the frontiers of our knowledge. It is a cosmic dance where each solved riddle often leads to a dozen new ones, pulling us deeper into the unknown. Perhaps the most prominent lingering question, the one that continues to fuel scientific debate and imaginative speculation among planetary scientists, is: what is the true origin of Iapetus's ridge? We now have a profound understanding of its physical characteristics, its monumental scale, and its ancient age. We have two compelling hypotheses: the faster spin theory, which posits a rapidly rotating plastic moon that solidified with a pronounced equatorial bulge, and the collapsing ring theory, which suggests Iapetus once possessed its own miniature ring system that eventually rained down onto its equator. Both of these ideas offer elegant, scientifically plausible explanations for its equatorial location and immense scale. But which one is the right one? Or is it perhaps a beautiful, intricate combination of both? Could an initially faster spin have created a pre-existing bulge, which then attracted ring material more efficiently? Or is it something entirely different, a process we haven't even conceived of yet, waiting for a future generation of minds to uncover? The evidence for each theory, while strong and supported by models, is not definitively conclusive enough to entirely rule out the other. The heavily cratered surface of the ridge tells us its ancient formed very early in the solar system's tumultuous history, but it doesn't definitively tell us how it formed, what specific cosmic hammer struck it, or what primordial forces shaped it. Was Iapetus once spinning so fast that it almost ripped itself apart, leaving a fossilized bulge as a permanent record of its youthful exuberance? Or did it once possess its own miniature ephemeral ring system, a delicate halo of debris that eventually, slowly, gracefully rained down upon its equator, piling up into this colossal structure? These are profound questions about the very mechanics of planetary formation and evolution, questions that Iapetus, in its silent grandeur, holds close to its icy heart, waiting for perhaps a future mission or a sudden brilliant breakthrough in theoretical understanding to provide a definitive, unambiguous answer. For now, the towering wall remains a silent, monumental enigma, a frozen echo of a violent, distant youth, its story unwritten in its entirety. Another profound question, one that delves into the very composition of this enigmatic moon, concerns the material that creates Iapetus's peculiar dark face. What is the dark material of Iapetus's mysterious face actually composed of, beyond something simply carbonaceous? We know from Cassini's spectral analysis that it is carbon-rich, bearing a striking spectral resemblance to certain primitive carbonaceous meteorites found on Earth, such as the Murchison C2 meteorite. This link to meteoritic material is a powerful clue, suggesting an external origin from the primordial building blocks of the solar system. But carbonaceous is a broad term encompassing a vast array of organic compounds. Is it some form of simple primordial organic goo? A complex mixture of basic hydrocarbons, the kind of chemistry that might have preceded the dawn of life in our solar system? Or is it something even more exotic, a unique form of carbon, perhaps altered by billions of years of exposure to the harsh radiation and vacuum of space? Is it related to the fundamental building blocks of life, hinting at the ubiquity of prebiotic chemistry across the cosmos? Or simply the burnt, altered remnants of ancient cosmic dust, baked by distant sunlight, without a physical sample, without being able to run it through the sophisticated laboratories here on Earth, to subject it to the full battery of analytical techniques available to us? Its precise chemical fingerprint remains somewhat blurred, like a hazy photograph. It's like knowing a magnificent book is written in a certain ancient language, but not being able to read the intricate words themselves, only inferring the general subject from the occasional recognizable character. The subtle variations in its spectral signature, the nuanced way it absorbs and reflects light across different wavelengths, suggest a rich chemical complexity that we can only guess at from afar. To truly unlock this secret, to understand the precise nature of this dark, light-absorbing material, would provide invaluable insights into the composition of the early solar system, the evolution of organic chemistry in space, and the long-term effects of cosmic weathering on exposed surfaces. This chemical puzzle is a quiet challenge inviting future missions to finally taste the very essence of Iapetus's dark mystery. Unless we go there, unless humanity sends another dedicated mission, one perhaps designed not just to orbit and image with increasing resolution, but to land, to collect physical samples, to truly touch and analyze the surface of Iapetus with direct instruments, it will be difficult, perhaps impossible, to know for sure. The answers to these lingering, profound questions require a level of intimacy and direct interaction that our current technology and, more importantly, our current mission plans do not yet provide. And here lies a bittersweet reality, a quiet challenge to our persistent curiosity. As of now and for the foreseeable future, no missions are currently planned to sample or even circle this perplexing place with the same intimate scrutiny that Cassini once provided. Iapetus, for all its wonders and all the knowledge it has already yielded, remains beyond the immediate reach of our robotic explorers. It will continue its slow, stately orbit around Saturn forever, turning its two distinct faces to the distant sun, holding its colossal ridge as a silent, monumental testament to an ancient dynamic past. So for now, we remain in the dark about many of its deepest secrets, a fitting irony perhaps given its enigmatic dark hemisphere. After all, as we began this journey, Iapetus was once the ultimate vanishing act, a celestial magician defying immediate explanation. And a magician, as the old saying goes, never truly reveals their secrets completely, always leaving a tantalizing thread of mystery to draw us back for another ponder, another dream. This quiet, enduring mystery that Iapetus embodies is not, in truth, a failure of science, nor a frustrating dead end for human curiosity. Rather, it is a profound and beautiful invitation. It is an invitation to wonder, to stretch our imaginations beyond the comfortable boundaries of what we currently know, and to continue asking the big fundamental questions that pull us out of the mundane and connect us intimately to the vast, incomprehensible beauty of the cosmos. Iapetus, with its unique characteristics, its two-tone surface born of cosmic dust and subtle temperature shifts, and its impossible ancient ridge, serves as a powerful silent reminder of the incredible diversity and unexpected phenomena that await us in the universe, even in our own celestial backyard. It whispers to us that the cosmos is far more imaginative than our grandest theories, far more intricate than our most complex models. Think of the scientific endeavor not as a race to find all the answers, but as a perpetual journey of exploration. In this journey, encountering a profound mystery, a question that stubbornly resists easy explanation, is not a setback. Instead, it is a precious gift, a fertile ground for new ideas, new ways of thinking, and the development of entirely new tools and methods of investigation. Iapetus, in its serene distant orbit, perfectly embodies this spirit. It pushes us to think beyond familiar terrestrial geological processes, beyond what we understand about the formation of our own world and its moon. It compels us to consider the long, slow, inexorable work of subtle, persistent forces acting over unimaginable timescales, sculpturing worlds in ways we can barely fathom. It forces us to embrace the beautiful uncertainty of discovery, to appreciate that the journey of asking questions, of nurturing a sense of awe and curiosity, is often as rewarding, if not more so, than the final arrival at a definitive answer. The very act of wrestling with such profound cosmic riddles enriches our understanding, not just of the universe, but of our own place within it as curious, questioning beings. Iapetus stands as a testament to the fact that the universe is far more imaginative than we are. Our theories, no matter how elegant, how meticulously constructed, how beautifully they explain what we can observe, are often just stepping stones to even grander, more complex realities. They are like partial maps of an endlessly unfolding landscape. This moon, this vanishing act, challenges our assumptions and expands the very boundaries of our understanding of planetary science. It reminds us that even in the vastness of space, there are still worlds that hold profound, beautiful secrets, worlds that challenge our assumptions and expand the very boundaries of our understanding. Each unsolved mystery in the cosmos is like an unread chapter in a grand cosmic book, waiting for the right moment, the right minds to turn its pages. Imagine for a moment the incredibly complex interplay of forces that must have unfolded over billions of years to sculpt such a world as Iapetus. It's a tapestry woven with threads of gravity, light dust, and time unfolding silently in the profound vacuum of space. Picture the faint whisper of dust, carbonaceous particles infinitesimally small, yet inexorably carried by the gentle push of solar radiation across millions of kilometers of interstellar void. This cosmic drizzle, originating from the distant retrograde dance of Phoebe and its kin, gently, subtly lands on Iapetus's leading face, accumulating over eons, layer by imperceptible layer. This is the first delicate stroke in the grand cosmic painting. Then consider the subtle warmth of the distant sun, its light having traveled for so long, barely registering as heat to our human senses. Yet on Iapetus, this subtle warmth absorbed by the newly darkened surface is enough to trigger the sublimation of ice, a process of planetary self-sculpture. The frozen water, the very essence of the moon's composition, transforms directly into vapor, bypassing the liquid state entirely, like a ghostly breath rising from the icy surface. This process is slow, continuous, a quiet hum of transformation. The story continues as this newly vaporized water, no longer bound to the surface, embarks on a journey of its own. Imagine the movement of this water vapor across vast distances on a world with virtually no atmosphere, following ballistic trajectories, jumping impressive distances across the moon's face. These molecules in their silent flight are drawn like cosmic moths to a flame to the coldest available surfaces, the already brilliant, highly reflective regions on the trailing hemisphere and near the poles. Here, they recondense and freeze, adding new layers of pristine, dazzling ice. This phenomenon acts as a powerful amplifier, a positive feedback loop that intensifies the initial contrast. The dark areas become even darker as they shed their ice, absorbing more sunlight and sublimating more water. The bright areas become even brighter as they accumulate more frost, reflecting more sunlight and staying even colder, drawing in more migrating ice. Over eons, this subtle yet relentless process paints Iapetus with its dramatic, almost impossible two-toned appearance, a masterpiece of light and shadow, born from simple physics and immense time. And then woven into this already astonishing narrative is the monumental enigma of the ridge itself, that colossal, perfectly encircling wall of mountains. Is it a frozen relic of a faster, more violent youth, a primordial bulge solidified into an enduring monument, a testament to Iapetus's youthful exuberance and rapid spin? Or is it the ghostly remnants of a shattered ancient ring, a miniature celestial halo that once graced Iapetus's skies before collapsing onto its equator, slowly piling up into this astounding feature? Each element, each characteristic of Iapetus is a piece of a grand cosmic narrative unfolding silently, majestically in the cold vacuum. It is a story of creation, transformation, and enduring enigma etched into the very fabric of a distant world. This quiet yet persistent hum of mystery, this constellation of unanswered questions, is precisely what makes Iapetus so profoundly alluring. It's a moon that, even after centuries of observation and a dedicated spacecraft mission, continues to hold its secrets close, whispering them only in hints and suggestions. This refusal to fully reveal itself is not a barrier to understanding, but rather a catalyst for it. It pushes us to refine our models, to imagine new physical processes, to develop more ingenious ways of gathering data. It's a constant reminder that our scientific journey is far from over, that the universe is vast and full of surprises waiting patiently for us to uncover them. Iapetus, in its cosmic dance, is a silent teacher. It instructs us in the sheer diversity of planetary evolution, showing us that worlds can form and evolve in ways wildly different from our own familiar Earth-Moon system. It demonstrates the profound power of seemingly tiny persistent forces, like radiation pressure on dust, or the subtle effects of sublimation when they are allowed to act over timescales of billions of years. It highlights the intricate interconnectedness of celestial bodies, where the history of one moon Phoebe can directly influence the surface appearance of another Iapetus across millions of kilometers. It is a living laboratory, a cosmic experiment playing out in slow motion, offering invaluable insights into the fundamental laws that govern the formation and evolution of all worlds. Beyond the scientific insights, Iapetus evokes a deeper, more philosophical sense of wonder. It reminds us of the vastness of time and space, of the unimaginable scales over which cosmic processes unfold. It encourages us to cultivate patience, a virtue so essential in both scientific inquiry and in life itself. It shows us that beauty can be found not just in the familiar and the easily understood, but also in the strange, the anomalous, the deeply mysterious. There is a profound poetry in the idea of a moon that seems to vanish a world divided by light and shadow, encircled by an impossible mountain range. These are the kinds of cosmic stories that resonate with the deepest parts of our being, stirring a primal sense of awe and humility. The very act of contemplating Iapetus, of imagining its slow spin, its dramatic dichotomy, and its towering ridge, is an act of connection with the sublime. It's a form of quiet meditation on the grand scale of existence, a gentle reminder that we are part of something infinitely larger and more complex than our everyday lives. It encourages us to embrace the unknown, to find comfort in the questions that have no immediate answers, knowing that the pursuit of these questions is a journey of discovery in itself. This moon, this enigmatic wanderer in Saturn's realm, stands as an enduring symbol of the universe's boundless capacity for surprise, its inexhaustible creativity, and its quiet, constant invitation to keep looking up, to keep pondering, and to keep dreaming of what else might be out there, waiting to be discovered. The cosmos is a lullaby of unanswered questions, and Iapetus sings one of the most enchanting verses, a quiet melody that encourages us to simply breathe and wonder. And so, as we conclude this quiet contemplation of Iapetus, this extraordinary two-faced world with its impossible mountain, let its enduring mysteries settle gently in your mind. Allow the profound beauty of its unanswered questions to become a soothing backdrop to your thoughts, a gentle echo in the quiet chambers of your consciousness. We have journeyed through centuries of observation, from Cassini's initial startling deductions to the unparalleled revelations of the Cassini spacecraft. We have unraveled many of its secrets, understanding the elegant interplay of external dust and internal thermal processes that painted its dual face and brought its incredible ridge into sharp focus. Yet, as we stand at the edge of our current knowledge, Iapetus reminds us that the universe is a boundless ocean of discovery with depths still unfathomed and currents still unexplored. The enduring allure of Iapetus lies precisely in these lingering enigmas in the threads of its story that remain untied. It is a moon that, even after centuries of dedicated observation and a monumental spacecraft mission, continues to hold its deepest secrets close, whispering them only in hints and suggestions, much like a master storyteller who leaves the audience craving just one more chapter. This subtle refusal to fully reveal itself is not a barrier to understanding, but rather a profound catalyst for it. It pushes us as a species to refine our scientific models to imagine entirely new physical processes that might be at play on distant worlds, and to develop even more ingenious ways of gathering data across unimaginable distances. It's a constant, gentle reminder that our scientific journey, our quest for knowledge about the cosmos, is far from over. The universe is vast and full of surprises, waiting patiently for us to uncover them. One whisper, one data point, one profound question at a time. Iapetus, in its serene, distant cosmic dance around Saturn, serves as a silent yet powerful teacher. It instructs us in the sheer diversity of planetary evolution, showing us that worlds can form and evolve in ways wildly different from our own familiar Earth-Moon system. Our own world, with its dynamic geology, its oceans, and its life, is but one of countless cosmic possibilities. Iapetus demonstrates the profound power of seemingly tiny persistent forces, like the almost imperceptible push of radiation pressure on dust particles, or the subtle effects of water ice sublimation under a distant sun when they are allowed to act over unimaginable timescales, accumulating for billions of years. These tiny nudges over cosmic eons can sculpt worlds in astonishing and unexpected ways, creating features that defy our initial intuition. Moreover, Iapetus highlights the intricate interconnectedness of celestial bodies, even those separated by immense distances. The history of one moon. The distant retrograde Phoebe can directly and profoundly influence the surface appearance of another Iapetus across millions of kilometers of empty space. It is a beautiful cosmic demonstration of how the actions and histories of seemingly isolated worlds are interwoven into a single grand tapestry. It is a living laboratory, a cosmic experiment, playing out in slow motion, offering invaluable insights into the fundamental laws that govern the formation and evolution of all worlds. Insights we could never fully grasp from studying our own familiar planet alone. Beyond the purely scientific insights, Iapetus evokes a deeper, more philosophical sense of wonder, one that resonates quietly in the mind as the day winds down. It reminds us of the vastness of time and space, of the unimaginable scales over which cosmic processes unfold. Our human lives, our daily concerns, seem infinitesimally small against the backdrop of a moon that has been spinning and transforming for billions of years. It encourages us to cultivate patience, a virtue so essential in both scientific inquiry, where answers can take centuries to emerge, and in life itself. It shows us that true beauty can be found not just in the familiar and the easily understood, but also in the strange, the anomalous, the deeply mysterious, the things that challenge our preconceived notions. There is a profound poetry in the very idea of a moon that seems to vanish a world divided by light and shadow, with almost painted precision, encircled by an impossible towering mountain range that whispers tales of an ancient forgotten past. These are the kinds of cosmic stories that resonate with the deepest, most contemplative parts of our being, stirring a primal sense of awe and profound humility. The very act of contemplating Iapetus, of imagining its slow, stately spin, its dramatic dichotomy, and its towering, enigmatic ridge, is an act of connection with the sublime. It's a form of quiet meditation on the grand scale of existence, a gentle reminder that we are part of something infinitely larger and more complex than our everyday lives, something ancient and eternally unfolding. It encourages us to embrace the unknown, to find comfort in the questions that have no immediate neat answers, knowing that the pursuit of these questions is a journey of discovery in itself. This moon, this enigmatic wanderer in Saturn's realm, stands as an enduring symbol of the universe's boundless capacity for surprise, its inexhaustible creativity, and its quiet, constant invitation to keep looking up, to keep pondering, and to keep dreaming of what else might be out there, waiting patiently to be discovered, waiting to share its own silent, cosmic story. The cosmos is a vast, harmonious symphony, and in its grand composition, the gentle hum of unanswered questions forms a most enchanting lullaby. Iapetus, with its peculiar song, sings one of the most beautiful verses, a quiet melody that encourages us to simply breathe, to let our minds wander freely through the starlit void, and to surrender to the profound, soothing embrace of wonder. It's a reminder that even when the light of certainty dims, the glow of curiosity can illuminate the deepest mysteries, guiding us gently towards the serene shores of sleep.